Welcome to This Explainer. Have you ever found yourself wondering why the world's absolute biggest tech companies are literally ripping out their traditional air conditioning systems to replace them with liquid cooling? Well, the answer is absolutely fascinating. AI isn't just changing software anymore. It's fundamentally rewriting the physical rules of how our data centers are built, powered, and most importantly, cooled. Today, we're going to break down exactly why this massive shift is happening, how the tech actually works, and what it all means for the future of the internet. Okay, let's dive into this. Here's our roadmap for today. We're going to cover the AI heat problem, the physics of cooling, four major cooling technologies, industry adoption, the sustainability nuance, and finally wrap up with the future of green IT. Section 1. The AI heat problem. To truly understand the solutions we'll be exploring, we really have to wrap our heads around the massive physical energy constraints data centers are facing right now. So, why are tech giants ditching air cooling? For decades, we relied on a pretty standard model. We had raised floors, hot aisles, cold aisles, and just massive AC units blasting cold air over servers. It was the absolute gold standard. But suddenly, as AI has scaled up, that old model has hit a literal brick wall. And this staggering projection really tells the story. 945 terawatt hours. The International Energy Agency says global data centers consumed around 415 terawatt hours in 2024, but by 2030, that number could more than double to nearly 945. And here's the truly wild part. A massive chunk of that energy isn't even powering the actual computations. It's literally just being used to keep the equipment from overheating and melting down. The core of this whole problem is density. Think about it. A traditional server rack used maybe 5 to 20 kilowatts of power. Blowing cold air through that handles the heat beautifully. But look at a modern AI rack. Modern GPU clusters need 100 kilowatts per rack today, and industry roadmaps are aiming for up to 1 megawatt per rack before the end of the decade. AI concentrates mind-boggling amounts of heat into a tiny little footprint. At those levels, moving enough air to cool it becomes impossible. It's too hard, way too energy-intensive, and incredibly expensive. Air just can't keep up anymore. Section 2. The physics of cooling. And this brilliantly illustrates exactly why air has reached its physical limits, and why we have to turn to fundamentally different science. It all comes down to thermal capacity. Water transports roughly 4,000 times more heat per unit volume than air for a similar temperature change. Just think about that, 4,000 times. Instead of burning massive amounts of energy trying to cool down a giant room filled with air, you use a medium that is mathematically vastly superior at absorbing and moving thermal energy. Because liquid targets the heat source directly, it unlocks some incredible advantages. We're talking significantly higher rack densities and dramatically lower fan power consumption, mostly because servers no longer have to sound like roaring jet engines trying to suck air through the chassis. You get improved overall cooling efficiency, way reduced space requirements, and far greater scalability. You basically pack way more compute power into much less physical space. Section 3. Four major cooling technologies. Right now, there are four primary engineering approaches shaping the future: direct-to-chip, immersion, rear-door heat exchangers, and closed-loop dry cooling. Keep these four in mind, because each one solves the heat problem in a uniquely clever way. First up is direct-to-chip cooling, or cold plate cooling. This is rapidly becoming the industry's go-to solution. Liquid flows through specialized cold plates mounted directly on top of those incredibly hot CPUs and GPUs, so the heat is captured exactly where it's generated. The massive appeal here is that organizations get world-class cooling capacity, but they still get to maintain the familiar, standard rack-based operations they already know how to run. Now, what's really interesting about this slide is immersion cooling. It sounds almost like science fiction. The servers are literally completely submerged into a bath of specially designed dielectric fluid. And don't worry, it doesn't conduct electricity. The fluid absorbs heat directly from every single component, making it one of the most thermally efficient solutions on the planet. But as you can imagine, sinking your servers into a fluid bath completely changes how you do maintenance. So it's incredibly effective, but usually reserved for specialized, high-performance computing environments. The third option is the rear door heat exchanger, or RDHx. This is just an incredibly clever trick for retrofitting. Instead of cooling the chips directly, a water-cooled heat exchanger is installed literally on the back door of the server rack. As the hot air gets pushed out the back of the servers, this door strips the heat away before it can even enter the server room. It's highly attractive if you want to upgrade your existing facilities to higher compute densities without completely tearing everything down. Finally, we have closed-loop dry cooling. In this model, heat is carried away and rejected outdoors through closed-loop systems, but it does it without ongoing evaporative water consumption. If you're building a massive data center in a water-sensitive region or maybe a desert, this tech is gaining major popularity because it can practically eliminate the need for continuous on-site cooling water. Section 4. Industry Adoption. So, this isn't just theoretical whiteboard stuff. The largest platforms you use every single day are already running on this tech. Google has actually been using liquid cooling for its TPU systems at a staggering gigawatt scale since 2018. AWS has built custom direct-to-chip architectures just for enormous AI workloads. Microsoft is rolling out designs aiming for zero water consumption. Meta, Oracle, they're all making massive investments here. Liquid cooling isn't an experiment anymore. It's the absolute dominant reality for the titans of tech. But hey, you don't have to be a trillion-dollar hyperscaler to use this. Commercial availability is absolutely exploding. Co-location providers, companies like Equinix, Digital Realty, Aligned, and QTS, they're actually offering liquid cooling as a service now. That's a huge deal because independent enterprises can now deploy heavy AI infrastructure without having to design and build these highly specialized facilities from scratch. Section 5. Sustainability Nuance. So the crucial point is, while liquid cooling sounds inherently green, it really isn't an automatic silver bullet. Sustainability requires some really complex trade-offs. You have to balance water usage effectiveness with power usage effectiveness, carbon emissions, overall energy consumption, and even local climate conditions. For example, closed-loop systems save a ton of on-site water, but the electricity generation itself still consumes resources. Improving water efficiency doesn't automatically mean you get the best power efficiency. Organizations really have to analyze their specific location, their power grid, and their workloads to find the setup that truly minimizes their impact. Section 6. The future of green IT. Looking toward 2030, we're going to see rack densities climb even higher, with direct-to-chip becoming the unquestioned dominant approach for new AI rollouts. We're also seeing the Open Compute Project, the OCP, stepping in to standardize components so the whole industry can move faster. But honestly, the biggest takeaway is this. Cooling is no longer just a facilities or maintenance issue. It is a strategic business component. The future of AI isn't just about faster GPUs. It's about the brilliant, smarter management of the physical resources needed to run them. The challenges and solutions we've explored today are part of a massive, industry-wide movement toward responsible computing. If you want to dive deeper into the technical frameworks that make all of this possible, I highly recommend this incredible book, Making IT Sustainable: Techniques and Applications, published by Academic Press. It is written by Mikhail Glovtov-Sev. It provides a comprehensive, ultimate guide for professionals looking to lead the transition to sustainable IT. It really is an absolute must-read for anyone working in infrastructure. I'll leave you with this final thought. How do you see liquid cooling changing the future of data centers and AI infrastructure? When the physical limits of hardware dictate the shape of our digital world, how is that going to influence the incredible AI innovations of tomorrow? It's a pretty fascinating question to ponder. Thank you so much for joining me on this explainer. Stay curious and keep learning.